Hi everyone, this is Zheyue from Fudan University. Thank you for coming. I'm going to present our work, AEM Facilitating Cross-Version Exploitability Assessment of Linux Kernel Vulnerabilities. This work is done with Zhang, Yuan, Xinqian, Zhuang, and Yang from Fudan University and Jun from Utah University. As we all know, a large number of vulnerabilities are reported every year, but the patching and mitigation requires huge effort. So it's better to prioritize patching and mitigation for the high-severity vulnerabilities. Exploitability is an important metric used in vulnerability assessment. Commonly, the analysis assesses the exploitability through manually crafted exploits or leverage some tools for automatic exploit generation. Due to the huge search space, existing approaches are naturally template-based. To exploit a Linux kernel vulnerability, one usually starts with a proof-of-concept program. Then it needs to understand the capability of the vulnerability, try to achieve the exploit primitive, and finally perform the malicious behavior to complete the exploit. Here is a typical process for exploiting a use-after-free vulnerability. It first needs to explore different views of the freed object, then manipulate the memory layout to occupy the freed object, and finally trigger the malicious use of the modified freed object. It is similar to exploit the auto-bound access. The difference is that one needs to first explore the data such as the size of the out-of-bound access. Here are some related researches. They usually focus on solving the problems in different steps of the exploitation. As mentioned before, due to the difficulties in exploitation, they usually rely on template-based approaches. Things get worse for modern software since it usually has huge amounts of versions. As the most widely used open source OS kernels, each kernel has evolved into various versions. One vulnerability found on one version may also affect other versions. Assessing the exploitability of all affected versions can help the patch management and mitigate emerging attacks for exploitable kernels. However, analysts usually only consider one version when assessing the exploitability. Whether other affected versions can be exploited is still unknown. This is always a time-consuming, labor-intensive work and requires expert knowledge on kernel and vulnerability. According to our study, around 80% of the exploits were only designed for one particular version. About 50% of the exploits failed on at least one vulnerable version. We start with a running example to show why one exploit succeeded on one version but failed on other versions. This page shows the vulnerable kernel code of the use-after-free CVE. We
Can you unmute yourself? You stopped the sound. Can you unmute yourself? Zheyue, you need to unmute yourself.
Previous step. Here we try to trigger the dereference of this pointer to hijack the control flow of kernel execution, and finally finish the exploit process. From our study, there are mainly two reasons that lead to the failure of cross-version exploitation. First, code changes happen frequently from version to version. When these changes get involved in the exploitation process, the kernel can present inconsistent behavior on different versions. This may cause exploitation fails on some versions. Second, data structures involved in the exploitation process may also be redefined or modified at another version. This may change the specific memory layout, which is critical to the success of the exploitation. This leads to a new problem. Once the exploitability of one vulnerability has been demonstrated on one version with a given exploit, how to verify the exploitability on other kernel versions? In order to solve this problem, we propose a new philosophy: automated exploit migration. Instead of generating a brand new exploit, AEM tries to migrate the given exploit to a kernel version where the exploit fails to work. Our key insight is that the strategy employed by one working exploit shall generally apply to a different kernel version. This is empirically validated through our evaluation of real-world exploits. Before introducing the details of our approach, we need to talk about the problem scope. First, we define the non-mappable exploits are those ones whose original exploitation strategy cannot be reused on target kernel versions. This may be caused by the removal of necessary data of the code between two kernel versions. In this situation, one needs to find new exploitation strategies. Besides, we assume an exploit against one kernel version is available, and the given exploit can trigger the vulnerability on the target kernels. What's more, the exploit primitive is enabled by memory co-options, and we only target to migrate the exploit primitive since triggering the exploit primitive is already a strong evidence of the exploitability. Though our key idea is straightforward, realizing this idea is quite challenging. The first consideration is the perspective of adjusting the exploit. Since the kernel exploits are mostly C programs, and they leverage system calls to interact with the kernel, we adjust the given exploit through system calls and their arguments. However, we still face two challenges to succeed the exploit. First, we don't know which system call to adjust. Kernel exploits usually from large number of system calls, and they often take complex arguments. Simply adjusting all of them will lead to a huge search space and incur high complexity. Second, we don't know how to adjust this call. Blind attempts are impractical since kernel exploitation usually requires accurate memory layout and code execution context. The intuitive idea is to leverage the exploitation process on the successful kernel as guidance to run the adjustment. However, it remains unclear what guidance should be reused and how such guidance can overcome the differences across kernel versions. Recall that we focus on memory-related exploiting primitives. In principle, they are an accumulative result of the sequence of memory operations. Therefore, we target to adjust the memory operations in target kernel to align with the ones in reference kernel in order to trigger the same primitives. Inspired by this idea, we propose primitive-centric alignment-guided exploit adjustment. It mainly contains two parts. First, we only focus on memory operations depending on user data, and finally affecting the primitive. Second, we leverage the execution context of the memory operations as the alignment guidance. This page shows the workflow of our approach. We first treat.
What happened?
We can see your screen, like what you're typing on the meeting chat. You may want to close that window.
Oh, okay. So how can we close it?
Stand by. Yeah, we got it. You can go back to sharing your screen now.
The execution of successful exploit and identify the triggered primitive. Then we extract the critical memory operations in the whole process and organize them into a dependency graph. After tracing the execution of failed exploit on target kernel, we align the memory operations with the critical ones from successful process and find out which operation leads to the failure. This operation is identified as the migration target, and we try to adjust the exploit to reproduce it on target kernel. Note that only if all the critical operations are reproduced on the target kernel, we regard the exploit has been migrated successfully. In order to represent the key exploitation strategies of the successful exploit, we organize the primitive-centric memory operations as a graph. Specifically, the vertex is a unique memory operation with execution context, and the edge represents the dependencies among different memory operations. Here, we will step-by-step show how the graph is constructed for previous example. With the execution trace, we first locate the control flow hijack primitive and locate all memory operations it depends on in the same system call. Then find there is one memory operation in setsock OPT system call shares the same access address with the ones in send message system call, and the data read in setsock OPT is written in send message. And finally, we find that the data written in send message is read from the argument of the system call. With this information, we could construct the graph for the whole exploit process, as shown in this graph. Next, we will do the alignment. Note that all the operations in graph are annotated with the extension context. They will then be used in identifying whether the operations from failed exploitation are aligned with the critical ones. There are mainly two reasons lead to the alignment failures. The first one is that the memory operation happened in the target kernel, but carried with slightly different data level properties. And the second one is that the same operation is never executed on the target kernel. For the example, the first failure is due to the reason 2. The target kernel adds a new check in the process, and the operation reading the address of control flow hijacking is not executed on target kernel. As a result, the first migration target is to modify the exploit to bypass the check and execute this read operation. Then we will find the exploit fails due to reason 1. Though the read operation has been performed on target kernel, it does not access the correct data as we expected, so our next migration target is to let it access the expected data as the reference one. We have implemented a prototype based on Anger and S2E. Basically, we leverage S2E to trace the exploit execution and perform the adjustment, and leverage Anger to analyze the instruction trees. In order to facilitate the evaluation, we collect 78 real-world exploits from public databases, technical articles, and existing AEG projects. By taking at least 24 human hours to produce each case, we finally reproduce 28 exploits, and we take all of them in our evaluation. Detailed information of the dataset is represented here. Besides, we gathered a group of Linux kernels, including both versions targeted by the exploit and are reported affected by the vulnerability. That consists both mainstream versions and downstream variants. Totally, there are 210 pairs of Linux kernel versions and exploits. Among them, there are 28 reference pairs which the kernel version is targeted by the original exploit, and for 92 pairs, the kernel should be successfully exploited without any migration. For the left 90 pairs, they cover 15 exploits. Our approach could successfully migrate 56 of them. To understand the capability boundary of AEM, we further analyze why it failed, and there are mainly two categories. The first one is result from engineering issues. That's because the S2E engine does not support booting kernel with symmetric multiprocessing, which is necessary for exploiting race bugs. The left 23 are non-migratable exploits, mainly because the kernel configurations do not hold on-target version. The required functionality and critical data structures is unavailable, or require different memory management ways. Finally, we evaluate the efficiency of our approach when migrating the exploit. Note that AEM needs an average time of 661 minutes to migrate an exploit. From the table, we can see that the time mainly spent on tracing the execution of exploitation. We will further try to improve this. What's more, we can see that our approach could effectively filter out irrelevant memory operations. Besides, AEM only needs to adjust the given exploit 1.36 times on average, which further illustrates that our design could facilitate the efficiency. Thank you very much for listening.
Okay, thank you for the presentation.
I'm very sorry. The leading author can't present remotely due to pandemic, so I have to help him for this presentation, and I will try my best to answer the questions.
Okay, are there any questions? Yeah, go ahead.
Anil, IBM Research. I wanted to ask about exactly which type of modifications to the kernel you can handle. So from what I understand, the heap modifications, if there are more allocations, for instance, you wouldn't handle it because that goes into a heap function. For example, are there any other cases?
Do you mean what kind of vulnerability the tool can apply?
No, not what kind of vulnerability, but what kind of kernel modification. So between the version that you are adapting from to the version you're adapting to, are you handling?
The kernel version.
So let me rephrase. You had an amazing table where you showed how individual parts are for those that have failed, what the reason is why they failed. Do you have the same table for those that succeeded? Like your second to last slide. You showed the cases why it failed. We want to know why it succeeded. What are the reasons for success?
Okay. The tool we present is EXP scope, and we extract the EXP graph for each exploit on each kernel version, which contains all memory access, which can represent the procedure of the exploit. So following the ESP graph, we can find the difference of the procedure of the exploit in different kernel version, and we can adjust the syscall arguments to make the ESP's graph of reference version and the target version the same, so we can succeed the migrate.
Okay, thank you. We'll take any additional questions online. Thank you.